Right. So today we are doing contingency tables, meaning one variable qualitative plus another variable qualitative. This qualitative variable, variable one, qualitative, variable two, also qualitative, and there can be several levels here, qualitative. Example, just now talk about physical activity, PA. We have regular, we have sometimes, and we have rarely, right? On this side, obesity, we have obese, yes, and no. Okay, all the rest, remove it, okay? So that's all you have. So you want to know, basically what you want to know is an association between physical activity, the level of physical activity, and obesity. Now, what do you expect here? What do you expect among those exercise regularly? Let's say I put A here, A percentage, and B percentage. Which one do you think will be higher, A or B? By right, regularly, A and B are percentages. Which percentage do you think will be higher, A or B?
B.
B.
B will be higher,
Yes.
right? Among those exercise regularly, not many. So we ideally must be this way. B must be more than A. Last one, let's say we call it X and Y. X and Y. Which one do you think we higher? All these percentage, which one do you think we higher?
X.
X to be higher than Y.
Y.
How to interpret now? How to interpret the two extremes? How to interpret the two extremes? How do you interpret the two extremes? Yeah. Supposing this is 10%, this is 90%, right? 90%. The total will be 100%, right? So this will be 100%. I'm just comparing percentages. This is, let's say, 80%. This must be
20.
20%. So total is 100%. Okay, the middle, let's say this is 50%. How much this must be?
50.
50%. So total will be 100%. So how to interpret this? How to write this in words, these findings? How do you write this? What's the finding here? What is the finding here? Someone tell me what's the finding? Say in words. How do you describe it?
Those who exercise regularly, they are less obese.
Less obese. One.
They are less obese or not obese.
Let's try this. Among those who exercise regularly, among those who exercise regularly, only 10% were obese compared to 80% among those who exercise rarely. Is it okay? Is this okay and is this agreeable? This explanation, is it agreeable?
Yes.
Yeah.
So ultimately, whatever you've done, you must be able to communicate. What the numbers indicate? Forget about center 1, 50, 50. We can say regularly, there are more sorry, the less obese, right? Those exercise regularly, the chances of being obese much lesser. But here, 80% of them who don't exercise are obese. What's my objective? What's my objective? Objective? What do you want? Objective is what do you want to know?
The association between the physical activities and the chances of getting obese.
Okay, to test the association between PA and obesity. Right? Next is, as you do earlier, as you do every time, analysis. So what test you did? In this case, will be chi-square test. Chi-square test. So in this test, we expect the results. Some p-value will come out. Let's say p-value, is it more than or less than 0.05? P-value, is it more than 0.05? Supposing p-value more than 0.05. So what's the conclusion? Right? This means there's no association. Right? And no association. To test there's an association, we click some buttons. If the p-value comes out more than 0.05, we conclude no association. And then what do you do? Stop.
You just leave it.
Stop.
Yeah, you just leave it.
Right. If the p-value is less than 0.05, now what do you say? Now what do you say?
There is association.
There is an association. Next question, how? How are they associated, right? They're not associated, we stop. They're associated, we won't explain in terms of percentages, not actual counts, percentages, right? So we explain here among those, right? So what's the conclusion? 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 Is there an association? Objective, the association, right?
Yes.
So answer will be what? Yes, there is an association.
Between PA and obesity.
Right. Yes, there is an association between this and this. How does it work? Those who exercise rarely are more likely to be obese. You don't have to do the percentage, more likely to be obese. It's a simple objective and simple conclusion, right?
Yeah.
Right? So that's all you want to know in this particular chapter. What is your objective? Physical activity and obesity. They are both qualitative. So what test? Chi-square test. What outcome? Whether p-value more than 0.05 or p-value less than 0.05. More than 0.05, stop. And what's the conclusion? There is no association between physical activity and obesity. We stop. If the p-value less than 0.05, we say yes, there is an association, and then go and explain how it works. That's exactly what we're going to do here. All right, let's go to the example. Data set 1.
Prof, I have a question.
Sure.
Would you go back to the demonstration you just showed?
Okay.
So for the analysis for this kind of data, I mean, if this was like without the table and it was just a statement, for the analysis, is it subjected to change?
From the analysis, subject change means what?
For example, right now we have a table. That's why we were saying it's a chi-square test.
Right.
If we didn't have a,
Ah.
if it was a question like assignment 2,
Right.
right, then it would have been different, right?
What test will you use, isn't it?
Yes.
Assignment 2. Just say chi-square test. That's all. See,
But
objective is PA and obesity, right?
yeah,
Knowing that PA and obesity are both qualitative, next question is, what test will you use? Chi-square test?
but is it subjected to be a different test other than that?
No,
Can it be? No.
only this.
So how about the correlation and regression test
No,
that we did?
that's only for quantitative variable. Later, I'm going to summarize this.
Oh, okay.
Right? They will summarize all the tests.
Because we have yes and no, that's why
Right.
it's qualitative.
Quantitative, right?
Okay, yeah. Okay, that makes sense now. Thank you.
All right.
Excuse me, Prof. I have one question.
Yeah.
Like for the qualitative variables, the number of levels does matter. Like one variable has 3 levels and another has 2 levels.
Okay.
Maybe both have 2 levels.
It doesn't matter.
Okay.
PA versus obesity. PA, how many levels? How many levels is PA now? Currently?
3.
Regularly, sometimes, and rarely. On this side, we have obesity. Yes or no, isn't it? Yes and no. I give a numerical example first. So what goes inside the cell are the counts, right? Isn't it? Let's say here, I took 100 people. Here, 150 people. Here, 50 people. So what are these numbers here? What is 100? Tell me what's 100? What is this 100 refers to? Come on. What is 100?
Total number of people
In the
who
sample, we took 100 people who exercise regularly, right? Isn't it? Class?
yes,
Yes.
What is this 50? What is this 50?
sample size for people who exercise rarely.
No. In this study, there were 50 people who exercise rarely.
Yes.
In this sample, 100 people exercise only sometimes. Right. Out of the 100 people, let's say now, 10 were here. Here must be 90. Right? So this total minus this value. Over here, let's say we have 50. Let's say here we have 30 or 20. Right. So this was the table. From the analysis, we get this table. Just click one button, they'll give you a table. So what does it mean here? Supposing the p-value is equals to 0.001. What's my objective? Objective?
Test if there is an association
Is
between
there an association between
PA and obesity.
PA and obesity? Right. Supposing p-value less than 0.05. Now what's your conclusion?
That yes, there is an association.
There is an association. How are you going to explain this table? How are you going to explain this table? If there is an association, must explain, right?
Yeah.
Let's try this first. Supposing p-value equals to 0.752. Now what's your conclusion?
There is no association, so
There
we
is no
stop there.
association. Right?
Yeah.
There is no association. Supposing the value comes out as this, the p-value. So this p-value equals to 0.001. Now what's the conclusion for second one? This number one.
There is
There is association.
There is an association. If there is an association, you must explain, right? Here, no association. You stop, nothing to explain. Here, there's an association, must explain, isn't it? Isn't it?
yes.
Yes.
Last week, remember, we discussed what are the names? I can't remember any names. Girirajan and me are related. What's the next question?
How?
How? Girirajan and me are not related. What's the next question?
Stop.
Stop. Here, related. Next question, how? Then you must write a statement. Write a statement. So what's the statement here? Come on, what's the statement? You're going to focus on obese or non-obese?
Obese.
You're going to focus your statement on obese or not obese?
Obese.
Obese, because that's a risk factor for other things.
Yes.
So how do you write it now? Can I say 10 of those regularly are obese compared to 20 here?
No, in terms of percentage, right?
No, because it's not significant. That's why. So you have to go with no.
So in terms of percentages, right? I can make this 200 and make this 20, 25. So who is more likely to be obese? Regularly or rarely? If the results comes like this, who is more likely to be obese? How many of those regularly are obese? How many of them regularly? There are 200 people. Out of that, how many are obese?
25.
25. There are 50 people who rarely, how many obese?
20.
So can I say those exercise regularly are more obese?
No.
Why not?
The percentage is less.
Percentage.
Because the marginal totals are different. The marginal totals are different. So you must express in terms of percentage. 25 upon 200, right?
Yeah.
Right.
12.5.
That's 12.5%.
12.5. So now let's say who's higher. Right? Sorry, right now. Among those exercise regularly,
Of 20 by, okay.
only 13% are obese compared to 40% among those exercise rarely.
Prof, can we just say the other way around? Like those who exercise regularly has a higher percentage of not being obese, and rare is the different case.
Okay.
We can,
Those-
right? As long as it sounds significant, right?
That means you want to go on this side, is it not obese,
Yeah.
right?
Yeah.
Now always we highlight the risk. The risk is obesity.
Okay.
Right? So focus on the not so good thing. This is a risk for other things. Our concentration is obesity will lead to something else.
Okay.
So what are the factors? PA. Does it work? P value less than 0.05? Yes. To explain this now, among those exercise regularly, only 13% obese compared to 40% among those exercise rarely. Is that okay?
Yeah, it does make sense. Yeah.
Right. Because ultimately, you're going to write. From young, started writing or started talking? From young, started writing or started talking?
Talking.
I didn't.
Talking.
And it started talking first or writing first?
Talking.
Talking.
So talk first, rarely, 13%. Right? And 40% among those who rally to the contrast. Regularly 13%. Rally 40%.
40%.
That's the association. Are we okay?
Yeah.
Now, can I break it up into 3 levels? Here we have 2 levels only. Obese, yes, no. Can I break it up into obese category? Let's say now. Okay, obesity. We have underweight. I can put here weight category. Underweight, normal weight, right? Overweight, and obese.
So
How
now
many levels now?
4 levels.
4 levels. So it depends how you define it. Here, define obesity, yes, no. Let's say cut at, let's say, 30. More than 30, BMI more than 30 years, BMI less than 30, no. Whereas here, I can divide into more categories.
Right.
Still the same test. Let's say I take out this. I remove this. I remove this. How many levels now? 2 by?
2 by
4.
4.
Right. We call it 2 by 2, 2 by 4 table. When people say 2 by 4 table, 2 rows and 4 columns. Understand?
Mm-hmm.
What is this dimension? What is this table dimension?
That one is 3 by 2.
3 by 2. When people say 3 by 2 table, we know that 3 columns and three rows and 2 columns.
Yeah.
So it doesn't matter how many columns you have and how many rows you have, as long as the total sample size is sufficient. Right? Are you okay?
It doesn't the groups doesn't need to be like higher or lower number or exactly the same number
Right.
as well. No need.
We prefer exactly same. Let's say 500 here and 500 here.
But
if we want to.
can it be 500 and then 300?
Right. So also can, because when you
Because
don't collect
the
data in the
percentage,
field,
right?
data in the field, right?
Yeah.
Very difficult to get the same number, right?
Yeah.
Right. So you collect whatever it is.
But it would be more accurate if you have the same number. But
Right.
still we can, because the percentage comes up later on.
Still we can. But supposing, look at this situation. This situation here, there's only 5 here. It's only 5. Then what do you do?
Well, I need to know how many
The
percent.
5, is it too few?
It's too low actually compared to the other ones. So I don't
It's too low compared to the other one.
Yes. So I don't think that's significant. Is there a range that we can maintain or at least?
Now you're going to look at one particular statistics. That's only assumption here. Right?
Yeah.
Only assumption, we have to look something like this, right? Expected count. This expected count must be at least 1 if your sample size is more than 100.
Oh.
This value must be more than 5 if small sample. Example, if sample size is less than 60. So that is the only assumption you're going to look for.
So how do we execute that?
Will come. Table where you put analysis and SPSS will come straight away. So this means at least one particular element is very low in number, isn't it?
So do we exclude it, sir?
No, hold on. We'll come to later.
Oh, okay.
So this kind of scenario, what do you do? Maybe we combine these two. Maybe we combine these two. So this become 155. This become 52. And this become 103. So you can eliminate this row. Right? So what do we name the row number 2? What do we name the row number 2? Is it only sometimes?
Some and rarely.
And sometimes or rarely. Then this will be accounted for. Right? We do that later. So number 1, doesn't matter how many columns and how many rows. Based on this, we can say the row times column table. We generally say R times C table. R times C table. R for row, C for column. One of the assumption is that the minimum expected count must be more than this. If not, as we did just now, combine the last two. The last two cannot be combined, then what do you do? The last two cannot be combined, then what do you do?
Can we exclude it?
Exclude it.
Okay, that's what I thought.
Right.
But it has to be a logical sense to
Right.
do this kind of
Include this.
assumption.
Right. So if I did just now collapses, I can say rarely or otherwise, right? Sorry, regularly. Regularly, this is not regularly, right?
Mm-hmm. Yeah.
Whereas the three groups, I still have to say three groups now. I still have to maintain rarely, sometimes, and regularly. If these two groups cannot be collapsed or combined together, in the analysis, we drop the last group. We won't consider this. Are you okay? That's what you do in practice. Questions?
Prof, just confirming, we look at the total, right, when we are talking of sample size?
Yeah, this total.
Okay.
This total is sample size. So normally for PhD, masters, we expect the sample size to be high for social sciences. Otherwise, results may not be representative. All right? For lab work, sometimes we can expect numbers to be very small in the lab testing. All right. Any other questions?
No, I don't think so.
All right.
I think I understand.
So it can be used for qualitative?
Yeah, qualitative. These are qualitative variables, right?
Yeah, quantitative.
For qualitative analysis, is it?
Yeah.
No.
Okay.
Only for quantitative analysis, where we have the numbers representing each levels. And here. These are counts. Counts are numbers, numerical. So they are quantitative analysis, not qualitative.
Yeah, got it.
Right. Qualitative analysis, you will not have a p-value. Only quantitative analysis, you'll have a p-value.
Wait, sir, this is not qualitative? Because yes
This
or
is
no?
quantitative, quantitative.
Oh, okay.
Are they numbers
They are
or
numbers.
alphabets? Numbers, right?
Yeah.
So this is quantitative.
Oh,
The
okay.
p-value comes based on these numbers.
Right.
For qualitative analysis, no p-value.
Oh, okay.
There's a p-value that is computed based on some numerical values.
Yeah.
So this is quantitative analysis. Questions?
No, I think we just need to make logical explanation if
That's all. That's all.
the numbers are tiny. That's it.
Right.
Yeah, sample
So
size.
statistics are more of telling a story, right? A logical explanation. That's all.
Yeah, got it.
All the analysis, a click button comes out. How to interpret them, that's all. Those days, you know how much work to go into to calculate the p-value, right? 2 by 2 easier. What about multiple dimensional tables?
Yeah.
But now, whatever it is, put inside SPS, click some button, some value comes out, interpret. Class it up. Have you done this? Have you done this? Any questions?
Yes, Prof.
Okay, now look at the results. Look at the results. What is this 33? How do you explain the 33? The column total, this 33 means what?
33 rarely exercise or worked out.
Say again?
33 people rarely worked out.
Right. 33 people rarely worked out. This 27 means what?
27, 27 people sometime worked out.
Sometime. This 48?
Regularly.
Class, yeah?
Regularly.
Regularly. You add this all, that's 108. Is it more than 100?
It is.
Your sample size, is it more than 100?
It is more than.
All right. How do you explain this percentage, 72.7%? How do you explain this? How do you explain that percentage?
Oh, that percentage means that those who rarely worked out and also sometime worked out, they both have a higher
Just
obesity.
this alone, the 27 alone. The
20.
27, say 72% alone, how do you explain this?
that means that out of 33 people, 72.7% of the people are figuratively are obese.
Now try again. 72.7% of those
who are rarely
Rarely,
rarely obese.
or obese.
72.7% of those exercise rarely obese.
Yeah.
Next one. So here we don't express the numbers. That's why I need the percentages. Why? These column numbers are different. Right. What about this next one? And explain this. And are you there?
Yes, I am.
Okay.
So in the second one, 77.8% of the total number sometimes.
What number?
Sorry.
Again, I'll tell the first one again. 72.7% of those who exercise rarely are obese. Finish.
Okay, so 77.8% of those who exercise sometimes are obese.
Obese, okay. Last one. Anyone? Sunita?
Among those who exercise regularly, 25% are obese.
Shall I use the word only? Only
Sorry.
25% obese?
Oh, no.
Yes.
Why
Okay.
not? Only. Why? This is 77%. 77% here. This only 25.
Yeah.
77 is about
Yes.
3/4, right? 77 is about
Yes.
3/4,
Yeah.
right? This will be 1/4, right?
Yeah.
Generally, what can I say? About 70% among those, or put the other way around. Only 25% among those exercise regularly are obese compared to 70% among those who do not. Is it okay?
Yeah.
Yes.
25% among those exercise regularly are obese compared to more than 70% among those who do not. Now, is that significant? Look at the p-value below. Is it
Yes.
significant?
Yes, it is.
Yes. So there is an association. So only 25% among those regularly are obese compared to 70%. That's missing. 70% compared to 70% among those who exercise only sometimes or rarely. That's all you want to know, right?
Yeah.
Right. And the method is very simple. It's the easiest of all.
Yep.
Click some button, value will come out, interpret. Now, below the second table, the last statement here, the minimum expected count is how much?
5.
5.
Less than 5.
12.7.
12.75. For sample size 100, this must be at least 1, right? Yes, I
Yes.
mentioned?
Yeah.
Yeah. The assumptions met. That's why, like exercise, your assignment number 2, if you ask the same question, PA and physical activity and obesity, right? This chi-square test, right? What's the assumption? The minimum expected count must be at least 1 for a sample size of more than 100, right? So that's only assumption. Very simple, straightforward.
I have a question about
Yeah.
the counting.
Hmm.
It says 12.75. So are we expecting to be higher than the?
Minimum is 1. Minimum.
Oh, okay. So if it's more than 1, then it's good.
Right. If you want to see this, I'll show you afterwards where to see, but normally we don't have to go and see it, right? This
Right.
summary comes out straight away. Later I can show you where to look for it.
Right.
Okay, look at the second example. This is job category and type of movie. Job category and type of movie, run the analysis. look at the conclusion.
Oh.
Do you get the same results? What's the p-value?
0.496.
496. Is it more than 0.05?
Yes.
Yes.
Therefore, what's your conclusion?
No association.
No
Just
association.
stop it right there.
Right. Now I'll show you what this minimum expected count means. Huh? So here, in your cells, click this expected count. Let's say close this, observed. Check this expected count. Continue. Click OK. Do you see the 12.75 in the table? 12.8, rounded up.
Yes.
Right. Okay, that's what you have there. Now, just watch this, or you also do. Now, go to obese here. The first one, number 1, just change the value to 3. Just one value, change to 3. Just change this to 3. And run the analysis again. Step. Run. Are you with me?
Yes.
All right, run. Okay, look at the value. And ask for statistics, statistics chi-square. So what's the minimum expected count?
0.25.
That's
0.25.
Oh, okay, I think I understand now.
That's a rounded value, okay?
Yeah, and also the cell percentage is less than 5. I mean, more than actually.
Right. It came because of this count very small. They're 0.25, 0.25. So in this case, supposing this is a real category, what do? Delete it or combine with something else?
Either one of those, if
Either
it's
one.
logical.
Right. Supposing 3 is towards obese, so I go to data, 3, change to obese, right? And run again. So run this now. Right, that count is clearly more than 1.
Yeah.
Significant. Now, just now, was it significant? With this, is it significant also?
Yes.
Yes. But the results are not valid. Why? The assumption is not met. Even though significant, the result is not valid. Right?
Yeah.
Now, it is significant and the results are valid.
Yeah.
So this is the easiest of all analysis with a minimal assumption.
Prof, are we not manipulating the data? I mean, like, is it okay to do this during our testing?
I'm showing here, okay, the 3 here. Supposing the 3 cannot be combined with this, then what I do? I delete the case number 1. Sorry, where is it? Supposing the 3, obesity, then I just delete it, keep it as missing, leave it as missing. Again, I do with the 3. So I get this output, p-value significant, but it's not acceptable because 3, only 1 count. I can't combine this with the others. Then I go to my data, delete these three, that means assume is missing, and run the analysis again. Now, is the assumption met?
Yes.
Is this significant?
Yes.
Now what has happened now? Sample size from 108,
107, I think.
107. Is it okay?
Yes.
Because now the results are valid, isn't it? Of course, bigger sample size better, but with a bigger sample size, the results are not valid. So sacrifice the one. Now 107, and my results are valid. That's how you report it. Questions? Questions? Okay, let's do an exercise. So objective is factors associated with diabetes. DM for diabetes, huh? Okay. Open up a table. Insert table. Okay. Variable. Variable. This is percentage. Oh, sorry, there must be one more. So this diabetes, non-diabetic. That's your chi-square. And that's a p-value. First variable, gender, female versus male. Okay, let's do this first and fill up this table. Can I put age here? Can I put age?
The variables for age is like there's a range, right?
And age
Quantitative.
is quantitative.
Quantitative, yeah.
So cannot.
Yeah.
Then age is quantitative, cannot. Gender. Let's do it. First step. So always, it's not, now which one goes to column, which one goes to the row?
The row will be gender, and then the column would be.
Why?
Yeah.
Why?
Because gender
Normally,
is qualitative, right?
No. Normally, what came first, he put in the row. Gender came first or obesity came first?
Gender came first.
Gender came first, right? Marital came first. Or
In
obesity came
DV, right, Rob? Is
Marital.
DV?
Say again?
Is it like IV and DV? IV always come first.
No, I don't want to call IVDV, okay?
Yes.
We don't know whether the cause and effect, right? Only cause and effect, you can talk about IVDV. Can I put age here?
No.
No, because it's quantitative. Can I put job category?
Yes.
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 Can I put marital?
Yes.
Yes.
Yes. What else? DM, physical activity?
Yes.
Yes.
So it's not necessary you must do one at a time. You can run them simultaneously. This obesity, can it be here?
No.
Obesity versus DM. We are talking DM now, right? Diabetes.
Yes.
Yeah. Can obesity be here?
No.
Why not?
It's quantitative. It's quantitative.
Oh, wait.
BMI is quantitative. BMI is quantitative. Obesity, yes, no, right? Check
Yes,
obesity. Obesity, yes, no, isn't it?
Oh, yes.
Obesity is can, but BMI cannot. Right. This hypercholesteremia, now we leave this one, okay? Demographic. Gender, job category, marital status, physical activity, and obesity. Statistics, chi-square. And cells, I'll choose row, observe, we don't need the expected, only observe. Row percentage. Why row percentage? Among the male, among the job category, among marital status, it says row, right? Row percentage. Continue.
That's
And click
supposed to be expected instead of observed.
come again.
Is that supposed to be expected instead of
Pick off the expected. We don't need this because this information will come below the table.
Oh,
Information, we can find it here, isn't it?
okay, it's already
Right.
there.
It's already there. Right, let's fill it up. Gender. Actually, who's talking behind? Who is that? Do you know who is this person? Is it this person?
I think it's
Okay. All right. Gender. Female.
right.
You understand what's DM? DM is diabetic. So gender, female. How many of them?
34,
34. Bracket
59.6,
9.6.
59,
59.6. So 59.6%. Right. Male. How many?
12, 23.5.
Right. Male 12. 12, that is 23.5%.
Yeah.
Non-DM 23, 40.4%. 39, 76.5%. Chi-square. That's a chi-square value, 14.362. And the p-value, so what's the p-value here?
0, all of them.
Don't say 0.
I mean, less than 0. Less than 0.00. Yeah.
So that's how I write the question. Right. So minimum expected count is clearly, what's the value? Minimum count, what's the value?
21.7.
21.7, sufficient. All right. So again, it's not necessary, you must do one at a time. I've run all the analysis one go. Next job category is here. Next marital status. Right. So just fill up these values.
Yeah.
Can you do it fast? Then you draw conclusions. Factors associated with DM. Let's say table X. Table X. Results from where heading. So you're talking about this subheading, and that's the results. Of course, you must type something to relate this to this. The chi-square tests were performed to test the association between set demographic variables. Variables and EM status. Table X. So don't just leave a table there. Table must have a heading. And there must be a short story. What is table all about? And what test is performed? So this test was performed, right? Performed to what? To test the association between what? Selected demographic variables and what? And DM status. So where are you showing the results? You're showing this table. So fill up the table, you're going to make discussions. I read fast. Any questions? Anybody, any questions? All right, fill it up. Your assignment 1, was it similar to this?
Yes.
Was it similar?
Yes.
Yes.
Except it was what? DBP, right?
Yeah.
Yes.
DBP is quantity or quali? DBP quantity or quali?
Quality, I think. Wait, what was the
Quantitative.
Quantitative.
Quantitative, diastolic blood pressure.
Oh, yeah, yes, yes.
Right. Exactly everything same. Here, diabetic status. Diabetic, yes, no. So it's chi-square. If this is diastolic blood pressure, which is quantitative, then this is going to be either t-test or ANOVA. All right, complete?
Yes.
Sir, I'm having a hard time opening up the SPSS.
Yeah.
Uh,
What's your problem?
just having a hard time opening up the SPSS, but I think I can read from here, I think.
Okay, right.
Yeah.
Okay. Are you in campus?
I'm actually home, so yeah, I'm using it remotely.
Okay.
But I do live near campus.
Are you in Malaysia or elsewhere?
I'm in Malaysia.
Malaysia, okay.
That's prof.
All right.
I think if I look at the table, I'll be able to answer.
Okay. Okay. And I think Shopee, they sell the SPSS very low rate. Shopee. Can you try Shopee?
They sell the software, is it?
Yes, yes.
Oh, okay.
Just try.
Oh, yeah, definitely.
Right.
Yeah, it's wow. There's a
Yep.
doesn't matter which one is it.
Doesn't matter.
So they have it for like $2.50. I mean,
Yeah.
2.5 ringgit.
Right. Okay.
Professor, for those who have no association, we no need to do the analysis, right? Do we need to mention that they have no association?
No. Just keep this table first. Get this table first.
Yes.
Complete this table first.
Oh, sweet.
Prof. Uzain has mentioned that his mic is not working, so he wanted to ask you if what does chi-square value signify?
Say again.
What does the chi-square value signify, or what does it mean?
Hold on. Okay.
One of the students is asking.
Okay, I'll come back to you. You're asking what the chi-square means, is it?
Yes, Prof.
All right. I'll show you an example. I showed the notes. Okay, maybe it's confusing. I'll show it here. Okay, what's OLS stand for? OLS stand for what?
Ordinary least square.
Ordinary least square. Ordinary least square of what? Ordinary least square of what? Yeah? When I say ordinary least square of what? What did you learn in the regression analysis? Least square of the residuals, right? Ordinary least square of the residuals, right?
Yes.
Right. Least square of the residual. What's the residual? What is residual? Hey, what's residual?
Those that
The points on the scale.
Unexplained.
unexplained, yeah, unexpected outcome, I guess,
Unexpected?
or what you call it, scattered, or
The distance between the line, the point and the line.
Come on, you're supposed to say in words.
Observed value minus the predicted value.
Observed minus predicted. So if I draw the line, that's a line. So what's residual? Residual is what we observe and what is on the line, right? So that's a residual, right? Residual, observed minus expected. So the word OLS stands for ordinary least square. Least square of what? Of the residuals. So the focus is on the residuals. Bigger the residual better, smaller the residual better. Bigger the residual better or smaller the residual better?
Smaller.
Smaller. Right? So OLS method means the line that minimizes the residuals. The line that minimizes residual. Again, OLS stands for ordinary least square. Least square what? Least square of the residuals. Got it? Got it?
Yes.
Right.
Yes.
Then what is chi-square? Chi-square. What is chi-square then? OLS. What's OLS? Ordinary least square. Right? OLS is ordinary least square. Ordinary least square. And what is chi-square? Okay, this least square is the square of the difference between observed and predicted, right?
Yeah.
Observed and predicted, isn't it?
Yes.
That's called the residual, right?
Yes.
Right. So OLS stands for ordinary least square, the square of the difference between observed and predicted. So chi-square means what? Chi-square what? That's a question must ask, right?
Mm,
Ordinary least square, next question is least square of what? Next question is square of what? Right? The answer is the square of the difference between observed and predicted. So what do you think chi-square will stand for?
mm. To determine whether there is
The word square, right? Square, isn't it? Here we have word square, right? Here also we have the word square, right? Isn't it? Square of what? Here square of what?
Residuals, right?
Residual. What is residual? What is residual? What is residual?
The difference between observed value and predicted value.
Therefore, here also same. The square of the observed and expected.
Oh.
This count is observed. What do you observe? That's expected. So this minus this, that's a residual. Do you get this value?
Yes.
Right. So that's a residual. Take the observed 33 minus 24.3, that's 8.7. So these are the residuals. Then what do you do with the residuals? Must you square them? Why square them? Why square the residuals?
To get the all positive values.
Because some are positive, some are negative. We add all this, you'll get 0. So you have to square the residuals. So here will be equals to This value, square it. Okay, that's a value squared. 76. Square this value as well. Do the same thing for the residuals. Are you following?
Yes.
All right. So that's the residuals. So these are residual values. Then what do you do? Look at the formula. What's the numerator? What's the numerator? This is the deviation, right? Deviation, isn't it?
Yes.
Bigger the deviation, bigger the chi-square, right?
Yes.
So bigger the deviation, bigger the chi-square. Bigger the chi-square, smaller the p-value, right?
Yes.
So small p-value, small p implies big chi-square implies there is an association. On the other hand, big P implies small chi implies no association. That's what it means. How small is small? How small is small?
Less
The
than
value less than 0.05 implies small p, right? P value less than 0.05. Big p value more than 0.05 implies big P. That's all you need to know. Where the chi-square came from? The difference between what is observed and what is expected. And then what do you do internally is squares and do some transformation using this formula. So chi-square can be big or can be small. Big chi-square, how do you know it's big? The P will be small. There is an association. P is large. There is no association. Is that okay?
Yeah.
Who asked the question just now? Of course, you can go deeper into it, but for you as a user, what the chi-square means? Chi-square actually means the deviations. Bigger the deviation means what? Bigger the deviation means there is an association. Some books also interpret this. They say, example, right? X does not depend on Y. Does not depend on Y. Here, X depends on Y. Now, we don't want to go into this because actually we can't say this because there may not be cause and effect. So rather say association whether yes, no. Some textbook will give this kind of explanations. Are you okay? Let me be asking, is there an association between diabetic and obesity? Some people may ask, does diabetic depend on obesity? We don't know whether cause and effect. We rather keep to the first part, whether there is or there is no association. We don't want to go into this yet. Are we clear? We don't have to know the nitty-gritties of the formula. Basically, that's what it means. A regression analysis, what is this numerator? Regression analysis, what's the numerator here?
observe and
Observed and predicted. That's the residual, right?
yes.
Here also, the numerator is the residuals, right? So that's all you need to know now. Okay.
Professor, I have a question.
Yeah.
Is there a value for this big chi-square?
There's no value. It can be zero. Start from zero to relatively to infinity. If it's zero, to theoretically to infinity, 0 to infinity. Right? You can go to that. There's no cut point. That's why we are guided by the p-value.
P-value.
Right.
Okay. Fine.
Of course, it depends on other things as well. The degree of freedom and other things. I won't go into that.
Okay.
Right.
Thank you.
Okay. Have we filled out the table?
Yes, Prof.
Okay. Next. What's the next variable? Job, right?
Yes.
Job, what's the p-value? For job, what's the p-value?
Less than 0.05.
So how much? How much the value?
How much?
0.007.
Right. This value must put exact value. Only when comes like that, we put this less than. Otherwise, put the exact value. Next. Next variable.
Marital status.
Okay, marital status. Okay, marital status. What's the p-value?
0.0292.
0.092.
Yes.
0.92.
0.92.
Yeah.
Correct or not?
Yeah,
Like
correct.
this, like this. Is it right?
0.092, Prof.
0.092. Okay. Next variable. You already fill up the table, right? What's the next variable?
Obesity.
Obesity. Right. P-value.
0.001.
Is it less than or just exactly 0.001?
Less than 0.001.
And only 0.001, you write there 0.001. Otherwise, obesity, right? Okay, 0.001, right?
Yeah, it's exactly 0.0.
Yeah, exactly 0.001. It's not less than.
Oh, sorry.
All right. Next variable. Is that all? What's the other variable?
Prof, but it is still less than 0.05. So
Yeah.
there is association, right?
Which one? Which variable?
Obesity, since it is less than 0.05.
Yeah. I want to fill up first.
Okay.
Physical activity, PA.
Oh.
PA,
0.93. 0.93.
0.093. Any other variables?
Nope.
It's all right?
Yes.
Right. The minimum count for all the table, is it sufficient? Minimum count? The minimum
Yes.
count, all okay. So now you're telling the results are shown in this table. Right. Among the tested variables, which variables are significant? Only which variable? Gender, job category,
Obesity.
job cat, obesity, anything else?
No. That's
No, right? So only number 1, number 2, and number 3 are significant. Significantly, no, normally write past tense, were significantly associated with DM. You can't leave it hanging like this. Since job category, you must go and explain first, right? Among the male and female, among the females, how many percent are obese? 59, sorry, DM, 59.6% are diabetic compared to 23.5% among the males. Is it almost half? Is it almost half compared? Twice?
Yes. Yes.
Twice, right? Compared to males. Job category, how does it work? Job category, maybe I remove this, put cells, right. Job category. Right, we say there's a significant difference. How does it work? Who is like standing out?
Nurse.
Nurses about 64%, right?
Yes.
And attendants and the doctors about 30%, right?
Yes.
Can I say this about 1/3? This about 2/3?
Yes. One
Right?
third. Yes.
So among the nurses, the attendants and doctors, about, I'll put here, right? About 1/3. About 1/3 of the attendants and doctors are diabetic. Right, to about 2/3. About 2/3 of the nurses. What else? Obesity. Obesity? What's the percentage? Obesity, 59. Right. 57, right? 57.9% of the obese respondents were diabetic to 5.5%. Again, not each line, just a paragraph. So you're telling, this is my heading, factors SLVDM. So what test you did? Chi-square test. To test what? Association between what? Demographic variables. Okay, they are all qualitative, and DM status qualitative. And the results are shown here. Show the results, and these are p-values. So whichever less than 0.05, first you tell them which variables are associated. Only gender, these were associated. Then explain each one how they differ. Right. Sometimes we call it univariate analysis. Later, going to use the same data for multivariate analysis as class. Now look at the two, gender and job category. Job category, who's more diabetic?
Nurse.
Nurse. How many percent?
63.9%.
63.9%.
63, Prof.
63. Okay, 63.
Yes.
But these nurses, are they mostly females? These nurses, are they mostly females?
Yes, maybe.
So what made a difference? Job category or gender?
Gender.
That's why from here, we're going to go into multivariate. because there could be confounding effect. Okay, multivariate. This is what you need for your PhD, not whatever studied so far. But to understand the multivariate, you need all these foundations. Right? You're telling nurses were more likely to be diabetic, but most nurses are females. So what made a difference? Diabetic, job category or gender? So you have to do multivariate. For multivariate, normally we use logistic regression, which I introduced last week. Questions? Okay, let's see what a test. Is anybody still doing this? Is anyone still doing this? Okay. So far, what tests have we done? Just summarize. So what test? So you need to know which test to use for which particular analysis. Right.
One sample t-test.
One sample t-test. Okay. One sample t-test.
Independent
Independent sample t-test. Right.
ANOVA.
ANOVA.
One-way ANOVA.
One-way ANOVA. Why is it one-way ANOVA? When I say one-way ANOVA, there must be. If I say one way, there must be another
Two-way.
two-way. If there's a two-way, there must be a three-way, whatever way, okay? But we start from here, we go to multivariate, then we call it multivariate ANOVA. Next, bad sample. Okay, this all is required for your assignment 2. Bad sample, and we did correlation. Regression. We did regression. And today we did chi-square. Okay, we did chi-square. Okay, let's see, when do we use all this? When to use what? Okay. So when do you use one sample t-test? When do you use one sample t-test?
And you have one population.
One population. The purpose? What's the purpose? Okay, now let's talk about population. How many population do we have here? Number of population, okay? Population. How many population here?
One.
Population 1. Yeah?
Two.
2. Yeah?
More than 2.
More than 2. Okay, this 2 is 1. Right. Next one. That.
2.
Why 2? The same people before and after, right?
Yes.
1. Correlation. The same people measured values. Example, EMI and BP. 1. Here's a 1. Here's a 1. Right? We consider the population. Right. What's the purpose of this test? Purpose of the test number 1. Purpose?
Test the means.
To test the mean in the population, right?
Yes.
Right. To test the mean in the population. Why single population? What is this? What's the purpose of this test?
Test the mean between two populations.
Okay, to test the mean difference between two populations. That's an example. This one. Another one. What's the difference? Yeah. What's the difference between independent sample t-test and another one?
Test the mean difference for more than two populations.
More than two populations. Extension is two. More than two, like 3, 4, 5, we do this. Bad sample. To test the change over time, right? Right?
Yes.
2 time points over 2 time points. It's called pad over 2 time points. Correlation.
To test the association.
The association between two quantitative variables. Quantitative variables. Is it cause and effect?
Yes.
Is it cause and effect? Correlation? Is it cause and effect?
No.
No. This is observation. To test the, I can say association, or you can say also causal. But I can still say to test the association between two variables. But more specifically, this is cause and effect. Cause and effect. All right, how much change takes place in one variable when I change another variable? Okay. Next one. Chi-square.
To test the association between two quantitative.
Association between two qualitative variables. All right. Assumptions. What's the assumption for the first test?
Cases are independent.
Right. Cases independent and fairly normal. Fairly normal, not very skewed. Next one. What's the important assumption? Independent samples. Assumption?
Variance in the two groups must be similar.
Right. Variances must be similar. The next one.
The same variance in the group must be similar.
Variances must be similar. Next one. Paired sample.
Distributed normal.
What must be distributed normal?
The difference
Difference.
score.
Times. Difference between times. Between two times must be normal. Correlation. What's assumption? Assumption again, the two variables must be normal. If yes, we use Pearson's chi-square, Pearson's. If not, we use, Spearman's. We won't run through all again, Spearman's. Right. Regression. What are the important assumptions?
Residuals must be independent and normally distributed.
Okay, as in above. Okay, normal. Second one, residuals must be independent and normally distributed. Okay, as in above, normal, or to this way line, it's been normally distributed. Right. Last one.
Yeah.
For n more than 100, normally this what you have. The minimum expected count must be more than 1. Okay, in our data, let's apply each one. In our data, where can we apply the first test? Where is opportunity to apply the first test? One sample, two tests. Give me an example. Example which you haven't done.
Get a mean value.
Say again.
A mean value equal to for any of the quantitative variable.
Now, give me the example. Example.
The mean of BMI is equal to.
Say again.
The mean of BMI is equal to.
BMI you already done. I want something else.
You want something else.
BMI you already done before. I want something else.
The mean of age.
Mean age. Equals to?
25.
Huh?
The mean of age is equal to 25.
25. Okay. Why BMI is 25? This must be 25. These are a bit older group, okay? 40.
Yes.
So now one simple t-test, one population, purpose is this assumption, and that's what you have. Okay, let's test assumption. What the assumption says? What the assumption says? Fairly. The assumption.
Normal.
Fairly normal, right? Fairly normal. Okay, let's test for normality. So there's a test, right? Fairly normal. Okay, tell me how to test normality. Normality for age. Somebody tell the class how to do normality. How to test normality. Anyone?
One sample t-test.
Normality, test normality. I'm testing this assumption. Hey, come on, how to test normality?
The p-value.
Yeah, I know how to test it. In SPS, how to test for assumption normality.
Compare mean.
Analyze.
Analyze.
Compare means.
No.
Descriptive.
Descriptive, explore. I'm testing normality. I'm testing the assumption. Fairly normal. Which variable?
Age.
Which variable? Age. Then what do you do?
Plots.
Plots. Ask for
Normality.
test. We also ask for histogram, CC, the distribution. All right, continue. And click OK. Look at the results. Is it normal?
Yes.
Homogeneous we know subfibrils.
KS.
KS. Is it normal?
Less than
No.
0.05.
Look
No.
at the histogram. Look at the box plot. Any major outliers, extreme values?
No.
No. Skewness?
Minus 0.17.
Is it close to 0?
Yes.
Is it
Yes.
quite symmetrical? Can I assume symmetry?
Yeah.
Yes.
Between plus or minus 1, can I assume symmetrical? As I
Yes.
said, fairly normal. This very small. From the box plot, I don't see any major outliers, extreme values. So I'll consider this is okay. All right, let's proceed. Next step, is the mean 40? Okay, how do you test this? How do you test whether the mean is 40?
Compare means,
Compare means,
one sample t-test,
sample t-test. Which variable?
age. Variable is age,
Test value?
40.
40. Click OK. Okay, look at the results. And the results. All right. What's the p-value of the test? What's the p-value of the test?
0.003.
Class, are you following?
Yes, sir.
Yeah. The results. So what's the p-value here?
Less than 0.003.
P is less than. Less than? Is it less than or exact value?
0.0.
0.003. 0.003. Conclusion? So what's the conclusion?
It's different.
The mean is not 40.
Right, it is not 40. Right, I think stop here. Of course, you can build a confidence interval. Okay, if not 40, then where is it? If not 40, then where is it? Okay, CI, confidence interval. So what's the 95% confidence interval? 95% confidence interval, how much?
Can we do
What
the-
must you do? What must you do to get a confidence interval?
Plus.
Hey, tell me. You don't tell me to do. You give me the answer.
40 plus
40.52
plus
to 52.59, isn't it?
Yes.
Yeah. Again, we want to know if the mean is 40, right? So one sample t-test. And assumption is this, that must be fairly normal. We determine that. The p-value of the test was 0.003, less than 0.05. Therefore, it is not 40. Then where is it? We are confident 95% is between these two limits. Does 40 fall inside the interval? Does
Yes.
40 fall inside the interval?
No.
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 No, it is not.
That's why it's not 40. If 40 falls inside the interval, then it is 40. The 40 does not fall inside the interval. All right, that is story number 1. Any questions? Any questions? Let's go to number 2. Independent sample t-test. When do you use this? Come on, when do you use this?
2 different populations.
2 different population. And that's assumption. Give me an example.
To test if BMI differ between
Don't say
gender.
BMI. BMI already done before.
To test between, to test the difference of DM between males and females?
That's what?
Diabetic
Diabetics is
between.
quantitative
Oh,
or
sorry.
qualitative?
No, it's qualitative with us.
Right. Another example, one variable must be quantitative. Other one, two groups. Two population occur, male, female, okay. But the other variable must be quantitative. That's what you said. That's what you said, age and BMI. So, gender and BMI. Gender, male, female, two variable, BMI is quantitative. But we already done this before. That's why I'm asking another example.
Gender and hypertension.
Gender and hypertension. Go and check hypertension. How is it measured in your data?
HPL. Yes.
Hypertension.
No.
HPT, yes, no.
No.
That's also quantitative. Yes, no.
We can say TG. We can check
Again? Again?
TG.
TG, triglyceride.
TG.
Is it quantitative?
Yes.
Can you try weight? Can you try height?
Yes.
All this
all the
possible.
three.
Right? Can you try a BMI redundancy? I don't want to do that. Can you do age?
Yes.
Okay.
Yes.
Right. Let me choose weight.
Wait.
So what do you want to know?
To test if weight differ
For
between
male, is it equals to weight for
Weight.
female?
height.
Is it okay?
Yes.
Weight male, weight for male, is it equals to weight for female?
Female.
All right. Okay, let's do the test. That will be, somebody tell me how to do it.
Analyze.
Comparison,
Compare
independent sample t
independent
test.
sample t-test.
Sample t-test.
Which variable?
Height. Sorry, weight.
Weight.
Test variable.
Which group?
Variable. Gender.
Gender. So define groups. How is it
Define
defined?
groups 1 and 2.
1
2.
and 2.
1, 2. Define group 1, 2. Continue. And click.
Okay.
Okay.
Okay. First, what must you test?
Normality.
Yeah, normality.
Variances.
P-value of variance.
Variances. We're talking independent sample t-test. Right? Assumption is variances must be equal. Are they? This table, one is test of variances, test of means. The test of variances, what's the p-value?
0.312.
Is it more than 0.05?
Yes.
Yes.
So this assumption, is it met?
Yes.
Yes.
Next, stay on the first row. What's the p-value for test of equality?
Less than 0.001.
Less than 0.001. Right. Conclusion. Are they equal? What's the question?
No.
Not equal.
Not equal.
Conclusion. Who is more? Who's higher?
Female.
Female higher compared to male.
Males.
Female higher compared to male. Right? So that's your test, purpose, assumption, an example here, and that's a p-value, sorry. Right. So that's a p-value. That means they're not equal. Conclusion. So females more than males. Maybe I take it out. Females more than males. All right. Are you okay?
Yes.
All right. How come others are very quiet? I don't know what's happening.
We actually taking notes, Prof.
We are here, sir. We are still here. We are listening.
Okay, I'll send this to you. Okay, I'll send this file.
Oh, yes. Thank you, Prof.
All right. Just observe first. You don't have to take down anything.
Yes.
All right. One way ANOVA. More than 2 population. Right? And
Yes.
here we have assumption. Okay, what do you want to know? Give me an example. More than 2 groups, huh? Give me an example.
Maybe
Huh?
weight according to job category.
Yeah, tell me in words. Job category and what?
Job
The
category. Weight,
Height was
Say again?
weight
height versus
depends
job
on
category.
job category.
Weight and
Job category.
job category, right? Weight by weight for nurses,
Nurses, doctor,
Doctor.
and
Attendance.
attendant, are they equal? Weight for nurses is it equals to attendant, it is equals to doctors. All right, let's do the test. Okay, somebody take me through the test.
Analyze.
Hold on. Let me close them.
Okay.
Okay. Analyze.
Compare means
Compare means
one way or another.
ANOVA. Okay, which variable?
Weight.
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 By
Job category.
job category. Then what do you do?
Post
Options.
Options. Check first. Don't go to post op straight away. Option.
or descriptive.
Descriptive and homogeneity
Homogeneity.
of variables.
Continue and click OK. Right. Is assumption met?
No.
Okay, now my time being, I assume yes, right?
yes.
Let's say we assume yes. All right. Assume yes. The means can read the ANOVA table, right? Yes means
Yes.
ANOVA
Yes.
table. If not, what must you do?
Non-parametric.
Non-parametric. Okay, let's assume this equal. Let's go into this. So what's the p-value here? Is it
Less than
0.001?
Yes.
Less than 0.01. So what does it mean?
At least one pair
At
different.
least one pair differ. At least one pair differ. What's the next question?
What pair?
Which pair?
Which pair or pairs? At least one pair differ. Next question is, which pair or pairs are different? So what must you do? What must you do?
Post-op.
Post-op test.
Don't straight away go to post-op. Confirm first there's a difference. Okay, post-op. Which test we used?
Tukey.
Okay. Continue. And click OK. All right. Now, who is different? How many asterisk signs?
3.
No, all.
How many asterisk signs again?
3.
3, yeah. Read carefully.
4.
No, 2.
4. There are 4 asterisk signs.
3, 4. Yes.
Divide by 2. 2, right? Why divide by 2? Attendant, nurse, attendant. That's a repetition, isn't it?
Yes.
Divide by 2. So which box has 2 asterisks? Which box has 2 asterisks?
Nurse.
Nurse.
The nurse minus attendant, is it positive?
Yes.
Nurse minus doctor, is it positive?
Yes.
What does it mean? Nurse, weight of the nurse is more than attendant and doctor, right?
Yes.
Right.
Yes.
So conclusion. So is there a difference? Yes. At least one pair differ. Which pair? Nurse more than doctors and attendant. Is there a difference between doctor and the attendant? Doctor, attendant, is there a difference?
No.
Doctor, attendant, no difference. All right. Shall we move on? All right. Next. Next.
Hair sample.
We can't use this data because there's no repeated measures. So we carry with this. Right. Let's go to next. Correlation. Give me an example. Give me an example. Example?
Weight and height.
Wait, age and height?
Yeah, weight and height.
Why you want age and height? It's all adults. As you grow older, going to grow taller. These are adults, not children. What are the variables?
TG and age.
Say again?
TG and age.
Okay, TG and age. Right. TG and age.
Sir, it's another row.
Oh, sorry.
Yeah, it should be there.
Okay, triglyceride versus age. All right. Let's test first whether they're fairly normal. How do you test normality? Again, how do you test normality?
Analyze.
Analyze, descriptive,
Descriptive.
explore.
And explore.
Which variables?
TG.
Age, and
then
TG.
TG.
Then plots, normality plot. Continue and click OK. All right. Is age fairly normal? Not too bad, right?
Yes.
What about triglyceride? Age, quite symmetrical. Triglyceride, is it skewed?
Yes.
Yes. Look at the box plot. Look at triglyceride. A lot of extreme and outliers, right?
Yes.
So this condition normal is not true. Then what must you do? This condition is not true, then what must you do?
Run Raman.
Do the Yeaman's correlation, right? So this assumption is not met. Okay, let's go to correlation. Analyze, correlate, bivariate. Why bi? Bi means what?
Two
variables. Bivariate. Which variables? Age,
TG.
TG. Here, Pearson and Spearman. Knowing that TG was not normally distributed, okay, let's check both. Comparison. Pearson's. So add this Spearman because I know TG is not normally distributed. Okay? Look at this table. This is Pearson 266. This is Spearman only 167, right?
Yes.
Is this significant? BMI, is it significant?
Yes. Listen.
Yes.
Okay. BMI, is it significant?
No.
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 No, now you must be very careful which test to use. Otherwise, it could lead a misleading conclusion. I can't use this because the variables are not normally distributed. So I must use this. So what's the p-value? 0.083. Okay, 0.083. So what's the answer? Are they correlated? No.
No.
Okay, no association between TG and H. That's why the assumption is very important. Okay, this should be below here. Right? This went through statements. All right. Next one, correlation. Correlation, regression.
Regression.
In fact, variables, again, this must be true, and this must be true. Example. Give me an example. So this must be cause and effect. One must cause the other.
Yes. Hypertension.
We have done BMI versus SBP.
Yes.
Give me another
Age and BMI?
H and BMI. So what do you think? The older people are obese or what? Is it true older people are obese?
Weight and BMI.
Weight and BMI, to calculate BMI, weight is used.
Which weight is it? Yeah.
Isn't it? BMI equals
Yes.
to weight over height squared. They cannot. Anything else? Look at the data. Anything else you want to test? Anything else?
BMI and HCl.
BMI and?
Hypertension. Oh, no, hypertension.
DBP and BMI.
DVP and BMI. Okay, we didn't do DVP earlier. Yeah, okay. DVP and BMI. Right. You want to know DVP versus BMI. DVP versus BMI. What do you want to know? You want to know, does DVP depend on BMI? Because it's causal effect. Right? It's causal. Does it depend on that? Okay, let's do the test. How do you go about this?
Analyze.
Regression.
Regression. Linear.
The dependent variable. DVP.
DBP.
Dependent variable.
BMI.
BMI. Just click OK. Just click OK. Look at the ANOVA table. The ANOVA table, what's the p-value? What's the p-value here?
Less than
0.01.
P-value is less than 0.01. What's the answer then? Does it depend? Does BP depend on depend on BMI?
Yes.
Yes.
Right? Next question is how, isn't it? How?
Yes.
Write the equation. Okay, write the equation. The last table here, write the equation.
58.197.
58.197.
Equals to 58, round it up, okay? 58 plus 1.14, 1.14, right? Times your,
BMI.
BMI.
right. So that's what I have so far. Of course, you can see the R square, 34%, right?
Yes.
So what does it mean? 34% of the variation in DVP is explained by BMI. Now, what about the balance 66%? What about balance 66%?
Other factors that we haven't considered.
Other factors. All right. So that's all we have here. Let's test assumptions. Continue. Right. Now, this is a recall button, okay? Every time put here, there's a recall button. Recall recently used dialogues. Click this. So all those are done is here. I go and select, okay, that's the one done recently. Okay, go ahead. I don't have to go to analyze all the time. Okay, plots. This for testing independent. So whether the set, predict, is here, that, the set, always here. Continue. And then save the residuals. Save the residuals. Continue. And okay. Right, look at the residuals. Are they random?
Yes.
Yeah. The dots are increasing like that, not random. So they are quite random. Independent, okay? Next.
Yes.
I want to test whether the residuals are normal. Explore. Now this, the last variable we created, residuals. Right. If the plots again, let's see whether normal or not. Continue and click OK. Okay, is it normal?
Yes.
It's not too bad, right?
Too bad, yeah.
Close to point.
This is okay. Skewness is okay. It's not too bad. Look at the box plot. There are some outliers, right?
Yes.
Yes.
Not extreme values. I think we can say it's fairly normal, right? You want to go for 0.05 exactly. The rounded up becomes 0.05, right?
Yes.
Right. So, okay. Assumptions are met. In our case, these assumptions are met. Therefore, this conclusion holds. All right. Questions? Let's go to the next one. Now you must understand this, okay? As an extension of your assignment 2, for each scenario, I'm going to give some data. So analyze it and report accordingly. The assignment 3, yeah?
Yes, Prof.
Extension will be an extension of extension of assignment 2, whereby for each scenario, I'll give you some data. So to analyze it and report accordingly.
Yes, Prof.
Okay, I'll give you on Thursday after you submit your assignment. All right, last one. Chi-square. When do you use chi-square? Qualitative variables. And that's assumption. And give me an example from the data, 2 qualitative variables.
Hypertension and obesity.
Hypertension and
Obesity.
HPT and HPT versus. All right. Are they both qualitative?
Yes.
All right. In layman's term, what do you want to know? Just layman's term, what do you want to know? What are you interested in?
Whether hypertension increases with obesity.
Increases. Yes, no, only word. Is obesity a risk factor for hypertension?
Risk factor.
Obesity, is obesity a risk factor for hypertension? Which is bad? Hypertension or obese?
Hypertension.
Is it okay to be obese? Supposing does not cause anything. Is it okay
Yes.
to be obese? Right.
Yes.
Is it okay
Yes.
to be hypertensive?
No.
No.
Right. Again, there must be a reason why you do this. That's why the scenario I gave you each one, right? Write the objective and so on and so forth. All right. Take me through. Analyze. Come on. Next. If I have to go to chi-square. You're all so quiet.
Cross.
Yeah.
Yes.
Descriptive.
Descriptive statistics.
Cross tab.
Cross tab.
Right. Reset. Reset, throw everything out. Reset. Okay, which variable? Hypertension.
Hypertension.
And
Hypertension.
obesity. Hypertension goes into column or row? Which one came first? Obesity came first, hypertension came first.
Obesity came first.
Obesity.
In the row. You know, it's not necessary this way, but normally that's why you do. So that you can ask for row percentage, meaning among those obese, how many percent hypertensive? Here, statistics, chi-square.
As well.
Okay. Right. So what's the p-value here? What's the p-value of the test?
Less than
Less than
0 0.05. The minimum count, is it okay?
Yes.
Yes.
The assumptions are met. The assumption is met. Okay. Assumption is met. The p-value of the test is less than 0.001. Right. What's the conclusion? What is the conclusion? Value column. Right. Conclusion? Is there an association?
Yes.
Right? Yes. Then explain. How does it work? How does it work?
For those who are obese, is
68.4% are obese.
Are
more likely to have
Having
hypertension.
8.4% of those obese
are
hypertensive.
having
Hypertensive, right?
Yes.
Or have
Yes.
hypertension. 68% of those who are obese have hypertension compared to only 23% of the normal ones. You must have this comparison. We can't simply say 68% obese are hypertensive. Compared to what? Compared to this? Can you say about 3 times more?
Yes.
3 times more.
Yes.
Right. Did I conclude? Yes. There is an association. How? Obese about 3 times, isn't it? 3 times more likely to be hypertensive compared to normal. 3 times more hypertensive compared to normal. All right. Did you do any other analysis besides what I discussed so far?
No, Prof. Prof, I have a question.
Yeah.
Yes. In the KS test, in the KS test for the two independent t-test,
Right.
if the p-value less than 0.05 and the skewness and the box plot is okay, can we assume it is fairly normal?
Yeah, fairly normal.
Yes,
I
it's
told you,
fairly normal.
so strict must be, right, more than 0.05. All right? Can say fairly normal, right? Supposing the p-value in the normality test, just now we talk about triglyceride. Triglyceride, check the triglyceride. P-value less than 0.05.
Yes.
This is very high, right? More than 1, right?
Yes.
And then histogram can see skew to the right, isn't it?
Yes.
And then we can see the box plot, a lot of extreme and outliers. So definitely triglyceride is not normally distributed. Are you okay?
Yes.
Okay, let me try DBP. DBP. Is it normal?
Yes.
Huh? Check again.
It's less than 0.05.
Is it less than or more than 0.05?
It's less than.
Less than. That means not normal, right?
Not normal.
But the skewness is not too bad, right?
Yes.
Okay, box histogram also is not very skewed. Box plot. Are there any major extreme values outliers?
No.
I still assume it is fairly normal. Fairly normal. There are other ways of testing this. Fairly normal. Okay?
Yes. Yes, Prof. Thank you, Prof.
One way is take the ratio between these two. How much is 358 divided by 233? How much is that?
358.
How much this value?
358 divide to
This value divided by this.
sorry, 358 divide to 1.5 something, 1.5.
Right. So another rule of thumb is this ratio less than 1.96. You can still assume fairly normal.
Oh.
Right. How is this value? Is it less than 1.96? This value, is it less than 1.96?
Yes, it's less than 1.96.
Right. You can assume fairly normal. So it don't have to be all the time the p-value, right? But for triglyceride just now, 1.9 divided by 0.2, definitely more than 1.96, right?
Yes.
Yes.
It cannot be normal.
Hmm.
The evidence, we should look at different angles as well. Right?
Yes.
All right. The last one we did last week was what? Logistic regression, right?
Yes.
Logistic regression. When to use this? When to use this? Again, one population.
Two quantitative variables.
Two quantitative regression.
Logistic. Oh.
Two quantitative regression. When
One
is
quantitative, one qualitative.
one quantitative example?
Quantitative.
If, example, test if, example, hypertension, let's say depend, right? So test the association with again causal effect. To test the association between qualitative
and quantitative.
And quantitative variable, right? Qualitative and quantitative variable. Okay, qualitative and quantitative variable. Quali and quanti is causal effect. One cause the other. Last week we did. But of course, It can be quali versus quali. We do later in your advanced level. Basically, what he did last week was, for example, we did obese, OB versus SBP. SBP. Why use DBP? What's the difference between this one here, marked in green, and this one here, marked in red? Let me change it to red. So what is the difference between these two?
DBP, BMI are quantitative.
DBP, quantitative, sorry, other way around, all out, whether DM, diabetes depend on BMI. What's the difference between this and this? For this hypertension, right?
Yeah.
The hypertension, HPT. What's the difference between number 1 and number 2? Number 1 and number 2, what's the difference? What's the difference? Here, DBP is quantitative. This is also quantitative, right?
Yes.
Over here, HPT, hypertension, is qualitative, isn't it?
Yes.
Yes.
BMI is quantitative, right?
Yes.
So BMI is the same. Here, DBP, quantitative. Here, hypertension is qualitative. Okay?
Yes.
That's the difference. Okay, let's do this. Analyze regression. Binary logistic. Why call it binary? Bi means what?
Two.
Two levels. Why? Hypertension. Yes, no. So 2 levels. Okay. So here, hypertension. And the variable is?
I.
Now, look at the screen again. Look at the screen. What's the difference between these two? Regression, these are dependent.
Independent.
Logistic, the same variable here.
Yeah.
Except DBP has been categorized into hypertension, yes, no. Isn't it?
Yes.
This is quantitative, the same thing. You cut points, you make it qualitative. All right. Run okay? The last table. What's the p-value for BMI? What's the p-value?
Less than 0.01.
0.001. Sorry, our 001. Okay, what does it mean? What does it mean? What's my objective?
HPT depends on BMI.
Depends on BMI. Hypertension depends on BMI. Yes. Next question is how, isn't it?
Yes.
How? How to answer that? How? First, look at this.
Variable in.
Yeah. What are you comparing here? What are you comparing? What's the reference group here?
1.
1 is what?
No.
No, reference group 0.
0.
Reference group. You're comparing no hypertension, right?
Yes.
What must you do? Change the coding, right?
Yes, the 0 is.
I want no to be 0, yes to be 1. Last week you did, right? Come on, just watch. I'm going to do that. Hypertension. Hypertension. Right click. Descending. This is no. No is number 2, right?
Yes.
Right. This becomes your reference group. And descending, ascending, the 1 is yes, right?
Yes.
What do you do? Change the nodes to 0 and fill it up. If you don't understand this time being still okay, just do this first. So now my coding, this 1, what's 1?
Is yes.
Yes. What is 0?
No.
So I go and label this hypertension. 1 is yes. I already changed the 2 to 0. All right. So I rerun the analysis, logistic regression. Click OK. Now check these values. So what are you comparing? Hypertension versus no hypertension, right?
Yes.
Right. Must be this form. Look at the last table now.
The equation.
BMI, is it positive?
Yes.
I don't write the equation positive. That's odds ratio. Is it more than 1?
Yes.
Right. So when BMI increases, the odds of hypertension increases. As the BMI increases, the odds of hypertension increases. So the write up, right, right, higher,
BMI.
BMI, higher,
The odds.
higher the odds of hypertension. Right. So we did a p-value, we did logistic regression. We call binary logistic. Binary because the outcome has 2 levels, qualitative and quantitative. This qualitative must be 2 levels. Okay, must be 2 levels. Right? The other variable can be quantitative or qualitative. Time being, just consider quantitative, cause and effect. Example, does hypertension depend on BMI? P-value yes. How to explain this? Higher the BMI, higher the odds of hypertension. How do you know this? Last table. So you have to consider this table. You're comparing hypertension versus no hypertension. This value is positive. Higher the BMI, right? So instead of using anything, higher the BMI. Is it more than 1?
Yes.
Higher the odds. Actually, this is odds ratio. I'm not sure whether anybody using this in your research. If anybody want to do this, let me know. If the outcome is binary, yes, no. Success, failure, pass, fail, right? Disease, no disease, these kind of things, right?
Yes.
Okay, there's one core in the class, right? What core? Is there a core in this class? Hello?
Sorry, Prof. Yes. Could you please repeat again?
Who's a core? Something core. Core.
Oh.
Who is it?
Hi, Prof. It's Hardeep Kaur.
Hardeep Kaur. Okay, Hardeep Kaur.
Yes.
Okay, I think you're the only one doing science. What's your outcome? What's your research on?
My research is on nanoemulsions. So I'm developing nanoemulsions of hyaluronic acid and kojic acid ester for antioxidative potentials for skincare and cosmetics.
Okay, what's the outcome of interest? What's the outcome?
So basically, I'll be testing on different parameters. Ones have already developed, and then check the efficacy and antioxidative potential of it,
Okay, efficacy.
and the antioxidative potential.
Yes, no, right? Efficacy, yes, no, right?
Yes.
Example, the vaccine, COVID vaccine.
Uh-huh.
Yes, no, isn't it?
Yes.
Okay, so you'll be using this kind of analysis.
Oh, okay.
The outcome is positive or negative,
Mm-hmm.
right?
All right.
Minus
Okay.
two levels.
All right.
So we have to learn more on this.
Yeah, well, I'll just have a look into it, and I might just need to ask you more questions about it then later.
Okay. That's why last week I told you, go back to your research area,
Yep.
download articles, and see what test analysis you have done.
All right.
The student texts me, she can't find any test, right? Again, never mind, you look for it, also testing, checking,
Okay.
testing, I'll let her know. So each
All right.
of you, right now, you must know what test you're doing in your study, right? Okay.
Thank you, bro.
Let's stop here now. Yeah.
Prof, yes, I just would like to review again about the logistic regression last week we done.
Okay.
Actually, last week what we did is that we compare BMI and SPP.
Right.
Then SPP is quantitative, therefore we convert SPP into quali by categorized as high and normal.
Right.
So we still can do that for the other quantitative, right, Prof?
Yes.
Yes.
What you're asking is, last week, okay, supposing we have this value here, SBP, right?
Yes.
SBP versus BMI. Okay, SBP versus BMI. Okay. People don't care whether 121 or 122. People may want to know whether high or normal. So I can ascend it. I can say these people are normal, isn't it?
Yes.
So I can code this 0. 0 means what?
Normal.
Normal. Let's say 140 until 140, let's say it's normal. Above this, let's say high. We use some cut points.
Yes.
All right. So now we can't do regression, linear regression, because categorized.
Yes.
So now you must do logistic regression. Now we have the SBP categorized. Where's SBP? SBP being categorized, right? Earlier, I could have done regression when this was quantitative. Now it become qualitative. So I had used this. So first I check this. The one is we define hypertension compared to low, high BP compared to low BP.
Yes.
Now look at this table. Higher the BMI,
higher
the odds of high SBP. Sometimes we do this.
Yes.
Or natural categories. What's a natural category here? Diabetic.
Yes.
Then that's a natural category. Okay. One more MC. Taking MC, will it depend on BMI?
Maybe.
What are you telling now? When I say medical leave, MC medical leave, depend on BMI. Why am I doing this? Why am I connecting medical leave versus BMI? They don't come to work because are they fat? They don't come to work. Is it because they're fat?
Yes.
Why fat means they don't come to work?
They have
Fat means
Fall sick often.
sick.
Fat means stay at home and eat.
Means unhealthy.
Unhealthy means what?
Take leave.
Yeah, unhealthy.
Oh, you fall sick.
BMI is one of the risk factor for other diseases. Because high BMI may be high cholesterol, high BP.
Yes.
Whatever. But you're taking this and this. Let's see. Logistic regression. The MC, medical leave,
Yeah.
does it depend on BMI?
Mm.
Right. So this is yes, MC, but no MC. Look at the results. Is it connected?
Yeah.
Higher the BMI,
Higher.
higher the odds. Why is it higher? It's more than 1. So BMI is one of the risk factors for taking leave. If you're a human resource manager, how is it helpful for you? Obese people tend to take more leaves. Not because obese, maybe other conditions. As a human resource manager, how's going to help you?
He will not hire the.
Don't hire the obese people. Right? Do not hire these obese people. Then your work will go on as usual. Otherwise, a lot of disruption. Okay.
Okay. Yes, Prof. Thank you.
Okay. See you all on Thursday. So by Thursday, submit your assignment 2. So I'll be sending data for each one of the scenario. You're going to analyze accordingly and report it. Right?
Yes, Prof.
Excuse me.
Okay, Prof.
Any questions?
Can we have the blog, the Excel? Can we have the Excel files?
Yeah, I'm sending now. Okay?
Okay.
All right.
And can we have the answer for the assignment 1 too?
Yeah. I'll send you. All right?
Okay, thank you.
Okay, bye.
Thank you, Prof.
Bye.